Hello and welcome to WQU University. This is the machine learning module. Alright, so let's go into my server, go into data course, into the machine learning directory, and the notebook we'll be using for today's lecture is the Intro to ML notebook. So there it is. Alright, let's go wait for that to open up. And as you'll see for these notebooks, there's two cell blocks at the very top of the notebook. Just run those. That sets certain things up for these notebooks, specifically with our images and certain key packages we use throughout all the notebooks. Alright, so let's talk about machine learning. So what exactly is machine learning? So machine learning is a broad collection of tools that finds patterns in existing data to make predictions on future observations of that data set. You can think of machine learning as some sort of machine that's going to ingest data, learn from those examples, and then can be further deployed for future observations. And it kind of makes sense because let's think about the way we learn, the sort of the natural way we learn. One of the natural ways we learn is that we experience something and then we take some lesson from that, some lessons from a set of observations. If we notice that grabbing the plate after it's been in the oven or been in the microwave, right after it's come out, we notice that grabbing that plate, it's rather hot, so we burn our hands. We learn something from that. So we learn from those observations such that in the future, we're going to be careful when we grab that plate. Very similar with machine learning. It's all about giving data a set of observations and having this algorithm, this model, learn from those sets of observations. Of course, as we go throughout this course, we'll see more examples, some more practical examples of machine learning. I'll talk about those. I'll show you some too at the end of this lecture. But there are really two things that really revolutionized machine learning in the past few years. One of them is just the amount of data that's been generated recently in the past few years is just a lot easier to generate tons and tons of data. And you could think of it we have a lot of people in the world, and a lot of people have access to mobile phones and computers, and that's just a treasure trove of generated data. So we have that increase, that exponential increase of data that's available for us, so we can train models, use models to learn from, such that to make predictions, or try to gain some sort of insight. But there's also been an increase in computer memory and performance. There's really, so what if you have a whole bunch of data, terabytes of data? If you don't have the computers and the memory and the computational and the computation to really generate and learn from this data, right? So those two things kind of came hand in hand to really revolutionize machine learning and made it practical discipline. All right, so let's see a very simple example of machine learning. So one thing what you're trying to do in machine learning is you have a data set X. You think of X as holding all the observations, but also the features or attributes of those observations. And what you're trying to do in machine learning is you're trying to construct a model F. You can think of it as a function, kind of mathematics, F of X, such that if you have that model, you give it an X, it will give you out a Y. So very, how you think of math functions, F of X. Although these functions we'll see, they don't have to be sort of like traditional mathematical functions. It can be something more abstract, but it's sometimes useful to view it that way. We're trying to find a model F to take X to make some sort of prediction Y. So for this example, we're gonna generate some data. So the first line we have here is using the NumPy's linspace function. This is a very common function we'll have to do. What does this linspace function do? What does it do? Well, what we're doing here is we're saying, okay, create a linear space from the number 0 all the way to 1, and we're going to have 100 values in that space. So this will generate a vector from 0 to 1 and of 100 values. Now what we're going to do here is that we're going to generate this data to have some noise. So this line of code here is going to choose an exponent, either 2 or 3. Just randomly choose 2 or 3, And the functional form we're going to impose to this data is x to the exponent plus some random noise. So that's what this is going to do. It's going to inject some sort of random noise, some error to our data set, to our y values. So let's just visualize that there. All right, so there is our data. It's a one-dimensional data set. We have x on one axis, we have y on the other axis. So now our task is, can we have some sort of model or function that can predict the y values, what we call the labels of our data set, given the observations, given the value for x. So one of the simplest things we can go ahead and do for this task is see if we can draw a line through the data points. See if we can draw a line through the data points, sort of a best fit line. We'll talk more about these algorithms later. But let's say that's just simply our task. Let's not worry about how it figures out the line, what's the best place to place it in our graph. But what we're trying to do is just trying to find a good line to draw through the data set. All right, we're going to achieve this here in this cell block here. So we're going to use this numpy function called polyfit. We are saying, okay, fit a line given our data set x and y. And then once we've generated that line, let's go ahead and plot it out. So that's what we do in the next block of code here. So we're going to plot the data, the actual observations, plot the values we would get from our fitted line, and plot out the true functional form. All right, so there are all those three things there. So notice the green one is the truth. The blue are our observations that we have, and this orange curve represents our best fit line. So essentially what we've done here is we've done linear regression. We use a linear regression model to draw a line through our data points. So some of the questions you might be asking yourself is, how good is this model? And can we add some sort of flexibility to the model, specifically if it doesn't do so well? Is there a way to tweak it to allow it to better adapt to the data? Another question we should be asking ourselves, is the model general enough? In other words, it might work fine for the data we use to derive the curve, to generate the model, but maybe it doesn't do such a good job with data we haven't seen before. Data that was not included in the training set we use to generate the model. And that's very important, because what if we have a model that does pretty well with the data we have, but fails horribly on future observations, on observations where we don't know the answer to, observations where we want the answer, we need the answer to. That's unfortunate, right? We want to make sure that we have some trust in how well our model has been generalized. And the last thing that we're interested in about this model is, what is this model going to teach us about the data? What are some insights that we can glean from our model? So for the simple test case, let's look at that last question. So we see here that our y label has a positive correlation with our feature label x. Okay, so within machine learning, there are two main branches. There's supervised learning and unsupervised learning. Let's talk about these two differences. In supervised learning, we're trying to generate a model to make predictions. We train a model with a data set X to be able to predict labels Y, that f of x relationship that we saw before. Kind of what we have here. This is a supervised machine learning task because we're given a data set X and we have a model that's able to predict what is the Y value, that label values. So that's all about supervised machine learning. There's further branches of supervised machine learning which we'll get into, but at the moment let's just focus on their supervised machine learning. There also is unsupervised machine learning. With unsupervised machine learning, we don't use the labels. We don't have labels with our training set. So because we don't have labels with our training set, the objectives for unsupervised learning tend to be different. There tend to be different applications for unsupervised learning. One application for unsupervised learning, or one thing unsupervised learning is used for, is to figure out groups or clusters within a data set. What are some natural groups or clusters that exist in our data set? Let's look at the results. Maybe we can generate some insight from that. Another example of unsupervised machine learning is we might have a data set with a large number of features, large number of dimensions, and is there a way to reduce the number of dimensions in a very efficient manner to keep as most of the information in our data set as possible? Those are applications of unsupervised machine learning. Now, I know that was a bit in the abstract, so let's actually, show a concrete example. So let's say you have consumer data, some information about your customers, things like their age, their hobbies, other products they have purchased through your company. And maybe one task is, can we take this data set, be able to train a model to predict whether they will buy some product or not. Given the way I framed this question, is this a supervised or an unsupervised machine learning problem? It's a supervised machine learning problem because we're trying to take some data set and be able to make predictions. In this case, we want to see whether someone will buy this product or not. So ultimately, there is a prediction. So every time we're trying to predict something, you should think about, oh, it's a supervised machine learning. Now, what if I asked you a different question? We have the same data set, this consumer data set. Things about their age, their hobbies, where they live, things like that. Attributes or features for each of our observations. Characteristics, if I can use that word. Then instead of saying, well, can we have a model that tells me whether this person with these characteristics will buy this product? I'm not interested in that. Instead, I'm interested in say, okay, can we identify certain groups, certain similar individuals that I can call a group or a cluster in my consumer data set? This is important because if I figure out key groups, distinct groups in my data set, then I can take that information and perhaps generate ads that are more tailored to those groups. For example, maybe I find within my data set there's a lot of my customers that tend to cluster around characteristics of a certain age range, and let's say 25 to 30, and they like the outdoors. Then whatever product I'm trying to sell them, maybe I should target ads to them that appeal to their youth as well as the fact they like outdoors. So I can better direct my marketing campaign to those groups. So you can see in that situation, I'm not trying to predict whether someone will buy something or anything like that. I'm trying to identify groups or clusters within my data set. And then with that information, I can go ahead and do whatever I want to do for some sort of downstream process later on. For this course, we'll mostly focus on supervised machine learning, but we will have lectures for unsupervised learning. We'll see some of those examples, some concrete examples of unsupervised machine learning. Okay. As we've been discussing before, the data that we have that we're going to use to train our models is in a structured format. Let's call it X. We'll often call it the feature matrix. And in this matrix, we have rows and columns, and the rows are going to correspond to all the observations we have in our data set, while the columns are going to correspond to the different characteristics, attributes, or degrees of freedom we have for our data set. And if we're doing supervised machine learning, our Y vector, remember we're trying to construct a model to predict Y, will be a vector. So one value corresponding to each observation we have in our training set. Okay. All right, so let's go ahead and move on and see certain difficulties that might arise when we're doing machine learning. All right, so I'm going to run this cell block here. So let's go ahead and take that model we had before, that line model. And we saw that it did decent. If I look at it here, if I go back up, it did okay, right? It did okay from the 0 to 1 range. Perhaps it could do better, of course, but all right, so it did okay. But let's see how well it would perform if we go and extend the range. See how general that model is. How general that model is, because that's one of the things we want. We want a model that is rather general, that doesn't that can work for different ranges. So let's go ahead and use our model to make predictions beyond our initial range. Instead of from 0 to 1, let's see how well it does from 0 to 2. Given this, we have that plot in the blue curve, and we notice it does a pretty poor job, right? It looks like it did decent from 0 to 1, but it does horrible from 1 to 2. So the model didn't generalize enough. It was heavily biased and not flexible enough to model this more complicated correlation with our data. So perhaps a line isn't sufficient. All right, so let's try to fix that. In our previous example, we just used a one-dimensional polynomial, so basically a line to fit the data. Let's go ahead and try to fix this problem. Let's go ahead and be very extreme and say, you know what? Previously, we only used a polynomial of one dimension, dimension 1, to fit the data. What if we use a polynomial up to 15 dimensions? What will happen? Think about what will happen if we go ahead and do that instead. So let's go ahead and plot our results as we do there. So we have our data in orange, and we have our resulting blue curve, so 15 polynomial term. So in other words, we have one term on polynomial, x to the 15th, plus some coefficient x to the 14th, plus some coefficient x to the 13th, all the way to x to the 0 power. So in this situation, you can think of our model as highly adaptive. Maybe perhaps a little too adaptive. What do you guys think, given this result? Do you think it's, do you like the way it performs with the data? So if I'm looking at this, it's like, yeah, it does a pretty good job, but perhaps too much of a good job. Because if we go back to our data, if we go back up where we generate our data, notice we added noise. Where is that? There you go. Notice we added noise. And this is, you might say, okay, well, why do we add noise? Well, it makes sense because you can think of any application. There's going to be some sort of error when we're collecting data. Some noise and error that's going to cause some deviation from a true model, from the true physics, right? You have probes. Probes aren't 100% accurate. There'll be some sort of error, some noise in the background. So be some deviation. And we want to make sure that our model is able to capture the signal but not capture the noise. Don't adapt to the noise. Don't learn from the noise. But in this example here, we understand, if we look at it, we can believe that perhaps our model is too adaptive. There's too many degrees of freedom to this model that it starts to not only capture the signal, but start learning from the noise. Start learning from the noise that's embedded in our data set. And that's a problem. Because if it's fitting the noise here, perhaps it's not going to do such a good job for observations it has not seen before, because it didn't learn from that noise. We want the model to learn from the signal and not from the noise. So let's go ahead and extend the range. Let's go ahead and notice we trained the model from 0 to 2. But let's generate data from 0 to 2.5. So extend the range. Let's see how well it does. And that's what we plot there, and we notice the blue curve is our model. Orange is our data set. And it does a pretty poor job. It's a little hard to tell, but what ends up happening is that our observations our predicted values for our model just blow up, go to very large negative values. That pretty much, this orange curve looks like a flat line. It's not a flat line, it's just the scale, the dimensions of the plot really obscure it. It had to encompass those very large negative values for our model. So our model does too well from 0 to 2, but wasn't general enough and just fails horribly when we go from look at the window from 2 to 2.5. So you think of it now, we have sort of the opposite problem. Before, a line wasn't sufficient enough. It was too simple. It underfitted the data set. And if we overcorrected and we say, okay, let's go ahead and use a polynomial with 15 degrees, then that becomes overfitted and it also doesn't generalize too well. So understand that, you know what, somewhere in between is a better situation. Somewhere in between is a good model that isn't too specific or too unspecific, that can best fit our data set, that's general enough to fit our data, but also do pretty well for observations we don't have the answer for, observations we don't have the labels for. So of course you can go ahead and tweak and play around with what's the best number of terms of polynomials to use to fit the data. That can be a bit tedious as you play around with those parameters, but later on we'll discuss more sophisticated methods or more general approaches to this problem of underfitting and overfitting, which is one of the key concepts of machine learning. Given a model, how do you tune this model such that it doesn't overfit but also doesn't underfit as well? And one of the things when we discuss further about these models, there are things called hyperparameters. And the reason why they're called hyperparameters is because they exist one level above regular model parameters. So for this simple situation where we're trying to fit a polynomial through the data set, the coefficients to these polynomial terms, those are the model parameters. For example, let's say we had a very simple model. In this case, we say y equals ax squared plus bx plus c. A, b, and c, those are the model parameters. Simple model parameters that when we fit the model, we're trying to discover what are the best values of a, b, and c to fit the data. So those are just regular model parameters. Hyperparameters instead are models that are values of the model you choose prior to the fitting process, prior to the training process, that will govern the resulting values of the parameters. Hence the name hyper. They exist above regular parameters and they control the resulting regular model parameters. They're set prior to learning. That's one of the key ways to know whether something's a hyperparameter. You set them prior to fitting, prior to training the model with some sort of data set. And as I said before, when we look more into these models, when we dive into these models, we'll discuss what are the hyperparameters, what are the hyperparameters are available to this model, and how do they work, how do they influence this idea of overfitting versus underfitting we discussed, this key problem we have in machine learning. It's important to understand how these hyperparameters work so you can best tweak them to get the best performance from your model. Okay, so that was a very quick introduction to machine learning. So for this course, we're going to use Python, and specifically we're going to use a Python package called scikit-learn. Scikit-learn is the key Python package for machine learning. So it's important that we get a pretty good feel for this package, be very comfortable using this package. And one of the reasons why I would argue that this package is very popular is because it's very easy to use. There's a very simple interface to it. And as we see more examples, you start picking up with this syntax with this package. But hopefully you can agree with me that it's a very intuitive to use package. So what scikit-learn offers, it offers basically, I guess, two things. It's going to offer machine learning models to use. But it is also going to offer a lot of nice functions and all nice tools that you'll need for a standard machine learning workflow. A lot of things that we have to do with our data set or some sort of pre-processing or post-processing that we could go ahead and write the tools ourselves in pure Python from scratch. But why do that? Why reinvent the wheel? These are common things that we need to do for most machine learning problems. Scikit-learn provides those tools for us as well. So that will save us a lot of writing code. Okay, so let's see an example of this scikit-learn interface, this application program interface for scikit-learn. So one of the things that scikit-learn is going to do is it's going to implement these machine learning models as classes. And then we construct objects from those classes, and then we train those objects, those realized models. Remember, classes, one thing you can view about classes, they are the recipe or a blueprint. So in this example here, we're going to import the linear regression model. So this is a model to do standard linear regression on a data set for predictive reasons, so supervised machine learning. So we're going to say from sklearn.linearModel import linear regression. And one of the things you might not know, but there's a very strong convention that custom classes, or the non-native classes in Python, they start with a capital letter for each word. So we can see this here. We know that linear regression is in fact a class and not something else. So scikit-learn is going to adhere to that convention, so that's very important. You should always adhere to that convention. Makes things easier to read, makes our code easier to read. Okay, so we have this linear regression class. So let's construct an object from this class. And that's what we're going to do in this cell here. We're going to create an object. We're going to call it LR. We're going to create this object from this linear regression class. Now, in that class creation, we're going to pass certain parameters when we create the object. We're going to say, okay, fit the intercept. We're going to set that to true. We're also going to set normalize equal to false. And we're not going to get into the details about some of these things here, what they mean. We'll talk more about that when we dive into these models. But a nice thing is that we can, with Jupyter Notebooks, you can easily look up the documentation for the things we're doing. For example, if you want to know how do you construct objects from linear regression, what other parameters we can set. As we set these parameters, what other options we have, just type the name of the class, put a question mark at the very end, hit the run button, and out comes out is a documentation, a doc string for this class. And this works for all other Python objects. If they have a doc string, it will return the doc string, so you can look at it, read it, and understand how it works. And we'll make very much use of this documentation. So we can see here what these things mean. So fit intercept, whether to calculate the intercept for this model. And notice the default value is true. Normalize, this parameter is ignored when fit intercept is set to false. If true, the regressor x will be normalized before regression. So it's going to normalize our data set. So notice the default value is false. Let's close that. Okay. All right, let's go ahead and run this cell here. All right, so we created our linear regression object. Okay, so now we create this object. Let's go ahead and train this model. You can think of this object represents the model, but we got to train it and fit it. In other words, we got to give it a set of examples, as well as the answer, the value, the label for those sets of observations, this x and y. So one thing that's can be a little annoying when you're working with scikit-learn is that our data set x needs to be 2 dimensions. So at the moment, if I type in x, this is my data set. Notice it's a NumPy array. With NumPy arrays, there is the attribute called shape, which will tell us the resulting shape of the NumPy array. So we see here that this X, our data set, has 100 rows. It's only one dimension. Remember what I said earlier about these machine learning models, what type of, we train the data set X and it's a matrix. So it's got 2 dimensions. You remember what those dimensions represent? So one dimension, the rows, represents the observations. And the columns, the second dimension, represents the characteristics or attributes for each of those observations. For example, let's say you're looking at you're working with a data set to predict home prices. Each house you have in your data set, that's going to be represented as a row, and each column represents a different characteristics or attributes you have for each of your observations. Things like for each house you have the number of bedrooms, the latitude, the longitude, how many floors, perhaps the median income of the neighborhood that house is in. All those are characteristics or attributes or degrees of freedom that belong to the observations. That information is going to be represented as columns in this matrix. And all the houses, each house is going to be a row in our data set. So we have this structure to form this matrix, rows and columns, rows and columns. So the whole point there is that notice our data set is just one dimension, just 100 rows. Scikit-learn wants a data set that has 2 dimensions, so we got to make sure we do some tweaking with that. A nice thing about NumPy arrays is that there's a reshape method with our NumPy array. So there's a reshape. Let's take a look at the documentation there. It says, okay, return an array containing the same data with a new shape. So we see the syntax there. It says we have to give it the resulting shape. So remember how our data set was 100 rows? So let's go ahead and say we're going to reshape the data set to have 100 rows in 1 column. And there it is. There is our resulting data set. And we can go ahead and verify by calling shape. And notice it has 100 rows and 1 column. Perfect. But is there a downside with the way we went about this, where we figured out how many rows how many rows it should have and just manually put 101? Any concerns with this manual approach? It's a little annoying, right? We have to figure out how many rows the observations already had, how many observations we have, and manually put that in. We could do something like this, where we can take the length of X. And that's we can do that as well. But the nice thing is that NumPy, we can go ahead and pass an argument of -1 when we do reshape. What does this mean? Is that every time we use -1, where we're telling NumPy, saying, okay, NumPy says, okay, how many rows should I have when we reshaped our data set? And all we say by putting -1 is we're saying, okay, use how many rows are necessary. I just wanted to have 1 column. So, all right, so say 1 column there, and use how many rows we need to have 1 column. So if we have 1 column, it's going to be 100 rows. And that's what that -1 represents. It's a bit cryptic, and I want to point it out. Let's say, for example, we want to reshape it to have 2 columns. Of course, we're not going to do this for our example, but let's say we wanted to reshape to have 2 columns. If we reshape it to 2 columns and we have 100 observations, then we're going to have 50 rows. Let's just verify that by calling shape. And there you go, we have 50 rows. Of course, if we say 3, let's see what happens. We get a value. We're saying, you know what? You told me I wanted 3 columns, but I cannot evenly divide 100 by 3. There is a problem. You can't have 3 columns. You can perhaps have 4, because we can divide 4 into 100. So there we have, as a result, 25 rows. So that's what the -1 represents. It's sort of a default value, telling NumPy, okay, figure out how many rows are required. Just make sure that there is any number of columns. And we can go ahead and do it the other way around. We can go ahead and say perhaps I wanted 25 rows, whatever columns I need to achieve that. There you go. So go ahead and play around with this if you still need some practice. Because we'll be making a lot of use of NumPy, a lot of reshaping when it's necessary. And we go back to our original array, it's just 100. So that's why we reshape. That's why over here we say reshape it to have how many rows are necessary, but it's going to have one column. And now we can go and fit the data. Alright, so this is where we see the how we train or fit a model with scikit-learn. We're going to invoke the fit method of that object, of that model. The two parameters that get passed when we call fit is the x and the y of our training set. So you think what's happening here is that we pass x and y, we pass the observations, as well as the labels, the answers, and then the model is going to fit and train from that, learn from that data, such that we can now use it to make predictions. Okay, so after we call fit, let's look at some of the resulting attributes for this model. So since we have linear regression, so if you're wondering what is the exact form for this model, it's simply mx plus b. That's what we have here. Okay. Hold on. All right, sorry about that. So I finished talking about the reshape. Let me just go back and talk about this fit method here. Okay, so once we're ready to train the model, we're going to invoke the fit method. And here's going to be our x, and here's our y. Our training data, our observations, with the labels for each of all the observations. So we're telling it, okay, fit and learn from the resulting data set. The model we're using is simple y equals mx plus b model. Let's say once we fit the model, we want to understand what is the coefficient, what is the slope, what is the resulting intercept for this model. Well, we can retrieve them because they are attributes to the model. In this case, they're called coef and intercept. And notice they end in an underscore. You might be wondering, well, why is that? What's the whole purpose behind that? Well, the whole purpose behind that is that scikit-learn has decided to take a convention that says that the attributes that are solved, that are determined after fitting or through the training process, during the fitting process, we're going to use an underscore for those attributes to let you know that, you know what, we only knew the coefficient, we only knew the intercept after we fitted the model, which makes sense, right? We don't know what m is and b is until we fit the model with a data set. So that's the convention it uses. So in this case, it says, okay, the slope that I best determined was about 2.5, and the intercept was about -1. All right, so we trained a model. As we said before, okay, once we have our trained model, let's actually go ahead and make predictions. And the way we do that is with our model object, we're going to invoke the predict method. Instead of the fit method, we're going to invoke the predict method. Now with the predict method, we only have to pass it the x values, which makes sense because once we've trained a model, we can pass an x and ask for the y. We're not training the model, so we don't pass x and y. We're just simply going to pass x. And as before, this data set that we want to make predictions has to be a matrix, has to have 2 dimensions, rows and columns. So that's where we're going to also invoke, once again, the reshape. Okay. So let me just break this down into 2 blocks. Let me call this here, copy that, paste it there, call prediction. Okay. So now I have a variable called prediction. You might be wondering, okay, what does this predict method return? What do you guys think? What do you guys think would be a logical data structure that our model is going to return our answers to? It's going to return them as a NumPy array. So we look at predictions, let's run that. And notice it is a NumPy array. NumPy array, and guess what shape it is? Guess what shape this NumPy array is? It's a NumPy array of 100, a length of 100. So 1 dimension, length of 100. So the resulting dimension of the predictions is based upon how many rows did our data set have when we called the predict method. This data set here has 100 rows, so it's going to come out 100 predictions. 1 prediction for each observation. 1 prediction for each row in the data set we passed when we invoked the predict method. Alright, so we have a NumPy array. Let's go ahead and plot the data. So we're going to plot the actual training data as well as the predictions from our model. Let's go ahead and do that, run that, and there it is. So we have a line that's been drawn through the data. And we saw before, we understand that a line isn't the best model for this data set. So let's actually try to do a better job. So one we can do a better job is by adding polynomial features to our data set. In other words, take our data, it's our simple one-dimensional data, and say, okay, well, now we have, let's fit a curve between x and x squared. So we can do that manually. We can extend the number of dimensions manually, no problem, we should be comfortable doing that. But why do it the manual way when scikit-learn provides us a nice tool for us to do that? We'll talk more about these tools as the class goes on, but we'll see an example here. We'll see an example here. We're going to use something called a polynomial features. This is a transformer. It's going to transform our data set. A transformer is anything that's going to do some sort of modifications or transformation with our data set to get it into the nice form or a better form for a machine learning model. So you can think of the first step for this problem is we have our raw data. We're going to expand the dimensions to our data set, and then we pass the resulting new data set, this transform data set, into our linear regression. And this is a 2-step process. It can be a bit tedious because we have to do the steps manually. We have to go and transform the data set and then train the model with the transform data set. Sometimes it's very nice we can encapsulate the entire process into one estimator. Now, I didn't mention this before, but I'll bring it up here. Estimators are the machine learning models, is the word that scikit-learn uses for these machine learning models. So we're going to create a machine learning model in a way that has 2 steps. We're going to transform our data set to include polynomial features, and it has at the very end a linear regression. We're going to encapsulate that all into one estimator. Alright, so we have this. We construct what's called a pipeline. We do this by using the pipeline class. We give it the 2 steps, the polynomial features, the linear regression. Let's go ahead and fit that model. Of course, we have to reshape it. Let's make predictions and see how well it fits the data. And there it is. Does a pretty good job of fitting the data there. So you might be wondering, okay, so yeah, it did a decent job, but let's see how well it does outside of the range. All observations it did not learn from. Alright, so to expand the range, this can go from, instead of 0 to 2.5, all the way from 0 to 4. See how well it does, and it looks like it still does a pretty good job of generalizing the data. Of course, if you examine in, there is some sort of deviation, which should be expected, right? it's going to do, performance is going to be less than with the data it trained from, the data it learned from. But for the most part, it does a pretty good job, especially compared to the other models. The other models that were underfitted and the other model that was overfitted. Right, so that was I would say, a rather quick introduction to machine learning, and we saw some of that common interface with scikit-learn. Now, through this course, we'll gain more experience with working with scikit-learn, so don't feel too bad if some of that syntax went over your head. We'll see more and more examples as we dive into the lectures. But what I want to do now is I want to show you some examples of the model that we already constructed and see how that works. All right, so what I have here is I created a machine learning model to make predictions whether someone would have survived the Titanic disaster. And what we have here is that this model is going to ask for certain characteristics of a passenger. It's going to ask for your age, your sex, your fare, your class, number of parents and children aboard, number of siblings and spouses on board, and where you embarked on the Titanic. So think about, for this observation, we're asking for characteristics. So given these fields, how do you think these fields are going to manifest itself in our data set? In other words, are these characteristics, are they columns, or are they going to be rows in our data set? They're going to be columns in our data set. Remember, the columns represent the characteristics or the attributes for each of our observations. So now we want to make a prediction. Let's say we want to predict whether, if you're 20 years old and you are a male and you paid, let's say, 45, I believe it's pounds, 45 pounds for your ticket. You were in third class. You had 0 parents and children on board, 0 siblings and spouses on board, and you picked up the ship in Southampton. So we hit submit. Let's see if this works. So underneath the hood, there's a machine learning model that's been trained beforehand. It's going to take this observation and run it through the model and tell us whether given these characteristics of that passenger, whether the model thinks this passenger would have survived or not. In fact, it's going to give us a probability. It says the probability of survivorship is rather low, around 12%, which, if we think about this, if we think about what happened during the Titanic, that they said women and children first, and I believe there was there's some classism going on. So if you're in a third class cabin and you're a male and you're rather young, well, not too young, but an adult, you probably didn't survive. At least that's what our model says. Your probability of survival is around 12%. Of course, this model isn't perfect. There are certain errors involved with this model. We'll discuss how you would characterize the errors with this model. But what I want to show you here is basically what happened is the model took a set of characteristics for an observations and made a prediction. So you might be wondering, okay, well, what was the data this model was trained on? And that's what I have here. I have in this tab an example of the data set the model learned from. So let's think about, what did the model do, or what type of information the model used to make a prediction. So what happened was that this model, we gave it a set of observations of different passengers we have information on. And with those passengers, we have whether they survived or not. We have what class they were in the cabin. We have information like their name, their sex, their age, number of siblings and spouses on board, their ticket, their fare, their cabin, where they embarked. That's all encapsulated into this data set. Now, I purposely open it up using a spreadsheet. So I want to show you how we have our data set, how it's structured. It's a structured data set with rows and columns. The rows are the different observations, and the columns represent the characteristics, the attributes we have for each of those observations. Now, you might be wondering, okay, I'm sounding like a broken record. I keep on saying rows and columns, number of observations, number of characteristics, but this is a very key concept. I want you guys to be very familiar with. We have a data set in a structured format, rows and columns, number of observations, number of degrees of freedom or characteristics or attributes for each of those observations. Now at this point you might be wondering, okay, so let's think about how did the model learn, or what is it doing to be able to make predictions? Because it has all these observations. And you can think of it very high level thinking. What is going on is that given these characteristics, maybe the model is learning that, you know what, given the data you gave me, it looks like if people are rather young and they were in third class, that led to that individual not surviving or not. So if you give me an observation that has those very similar characteristics, guess what? I'm probably going to predict that they didn't survive. And you saw the model give a very low percentage of survival. Maybe in this data set, the model is also picking up on something else. It's picking up some pattern, right? It's picking up some observation that if the person was rather young but was, let's say, a child, I say rather young, but I mean a child in this case. It's a child and maybe they were in first class, and then a lot of those people with those characteristics survived. So when you give me an observation, when I say me, I mean the model, when you give the model an observation that given the training data suggests that the person survived, then it would probably predict the person survived. So that's what it's doing. The model was able to ingest this data, pick up the patterns, learn from those patterns, and then use those patterns to make a prediction on a set of observations. So that's one application of machine learning. We can also do sentiment analysis with machine learning. So this is another model I cooked up. So for example, one of the things we'll see in this course is how do you work with text data. Working with text data is we have to do some sort of pre-processing to get in a form for our model to ingest and learn from. We'll discuss those methods in future lectures. But let's say I want to be able to take some text and figure out whether it has a positive or negative sentiment. In other words, is the text describing something good or something bad? Let's go ahead and test this out. So let's say I'm going to insert a product review, and I say, okay, this product sucked. So I'm going to say this product sucked. It never worked from day one. I am so disappointed. It's like I misspelled disappointed. All right, I think I spelled it right. I am so disappointed, and I will not. And this was a ripoff. I want my money back. All right, I'm gonna hit the submit and see what the model says. And notice the model predicted, it's very hard to read. It says negative sentiment. It took that text and was able to determine that this text represented a negative sentiment. Let's go back and let's put a different sentence. Let's say this product was amazing. I would definitely recommend it to my friends and family. I am so happy with it. And it says a positive sentiment. So let's go ahead and think of a very high level. What do you think is going on? What do you guys think is going on with this model? How do you think it works? Let me ask you this. What do you think? Do you think this is a supervised or unsupervised problem? Is it supervised machine learning or unsupervised machine learning? It's supervised machine learning because it made a prediction, said whether it was positive or negative sentiment. And what is happening here is that you could think we trained the model on a large collection of text, review data. And we flagged those review data, and then we marked it. In other words, we labeled it. We said, okay, these reviews are positive, these reviews are negative. Try to pick up a pattern with that text data. Try to understand what distinguishes a negative review with a positive review. Understand that pattern. Understand that behavior. And once you've learned that behavior, once you've established that concept, that idea, go ahead and we're going to give you future text where we don't have the label, we don't tell you whether it's positive or negative, and tell us, given the observations, given the patterns that you learned, is it positive or is it negative? And what do you think are the patterns that this model picked up on? Very high level. I'm not asking for anything specific. We'll delve into this in future lectures, understand exactly what's going on, the nitty-gritty details. But you can kind of pick it up with those test examples that I wrote out. A lot of bad reviews, they probably have words like, this product sucked, or things like, I want my money back, or this is terrible, what a ripoff. So our model is probably picking up on that. It's probably picking up on that pattern. And good reviews, on the other hand, say things like great, amazing, wonderful, things like that. It's picking up on that pattern. And once it learns from that pattern, then it could take a test example and figure out, look at the word usage, look at the frequency of those words, and be able to make an assessment whether something is a positive or has a negative sentiment. So that's what's going on here. And I decided to show you guys so you can see a concrete example of machine learning models, and we'll delve into these. Like I said, I keep on saying, but we'll get into more of the nitty-gritty details later on. This is just an introduction. We'll build more of this intuition as the course goes on. Okay, so with that said, that's coming to the end of today's lecture, What I recommend is just go through this notebook, play around with it, understand the steps that are involved. One tricky point is this reshaping issue. Just make sure that the data set that scikit-learn wants has to have rows and columns, has to have 2 dimensions. So you might have to reshape your data such that it fits. A nice thing about scikit-learn is that with this linear regression model, it's a very simple model, but if you want to use a more complicated model, it has a very similar interface. You have the class, you create an object from that class, you fit the resulting object with an X and Y data set, and you make predictions using the predict method. The same interface. You can swap out the model, use a more complicated model. Of course, use a more complicated model, there's more responsibilities, a little harder to get to really make it work properly, and we'll discuss that when we get more into these models, but it's a very similar interface. And think about the concept we talked about, the underfitting, overfitting. This is a key concept that will be brought up over and over again as we go through this course. This idea that we want our model to be generalized enough, not too simple, but not too complicated, enough that it can not adapt to the noise, but be able to pick up the signal, pick up the relevant information, data, the relevant patterns that are able to make the model work with observations it has not seen before, observation has not learned from. So with that said, that's the end of the first lecture. Take care, guys.